Welcome to the 40th lecture in this series. So I'll continue with my discussion of vector fields. In particular, we'll talk more about Lie brackets of vector fields. So last time, towards the end of the last class, I'd talked about this simple algebraic properties that the Lie bracket is bilinear, in the sense that if I fix one vector field and it's linear in the other slot. So here I've written it just for the first slot, but then it's also antisymmetric. That will imply it's linear in the second slot as well. There is another crucial property of the algebraic property of the Lie bracket of vector fields, which I'll call the Jacobi identity, which I'll mention in this lecture or perhaps the next one. Now, in the end of last class, I had started deriving an expression for the Lie bracket in local coordinates. So let me just complete that. So we had reduced it to x can be written as sigma ai del by del xi, y can be written as bj del by del xj, where ai, so let's recall that ai and bj are functions from the open set, the chart to R. So, and using these bilinearity properties, one reduces the expression to this. It's a double summation over I and j, and then one has this. So let's see what this is. So ai, let's look at an individual term, bj del by del xj. Now let's act it on a function and see what we get. So this by definition is, I'll use the, for simplicity of notation, instead of del by del xi, I'll put del I. So this is, let's keep this notation in mind. So this becomes ai del I and then of bj del jf minus bj del j of ai del I f. One uses the Leibniz rule two times, and then one gets ai. So here I'll get ai bj del I del j f minus plus ai del I bj del j f, and then the second thing, which is bj ai del j del I f plus bj del j ai del I f. This, the first term in this and the first term in this cancel out. Notice that I have del I del j f, and here I have del j del I f, but these two are equal. What one should remark is that we know that mixed partial derivatives are equal in Euclidean space. However, these are not, when I say del I or del by del xi, I don't quite mean the Euclidean partial derivative. I am working on the open set U in the manifold. So del by del xi, as usual, is the pullback under the chart map, derivative of the chart map of the usual del by del xi. However, this thing this equation, equality of mixed partial derivatives, continues to hold in the manifold as well. This is true in Euclidean space and this is true in the chart. So these two things will cancel out, and I'm left with ai del I bj del jf plus bj del j ai del I f. So this is, I'll write summation over ij, and this is summation over ij as well. Now I want to have the same, recall that we obtained all this by acting on f. So here I have del jf and here I have del if. I want to get the same index for both of these. So I can just switch I and j in this, it doesn't matter. Or I can switch I and j in the first one. Let me do that. Summation over I and j, because both I and j run from 1 to n. And this sorry, yeah, this is not, what I have here is not quite right. So this is just the individual term. So what I have written here, the summation, is actually the full Lie bracket, not the individual term. So xy, here I should write xy equal to this, the thing again. So this is xy, and this is this, and here I'll get, I interchanged I and j, so aj, and this was a minus, aj, and then here it was del j bi del if minus the same term, and then finally I wrote it as a j del j bi minus bj del j ai, and then del by del xi. So this thing here, it was acting on f, and if I don't want f in that, I'll just write it like this. So this is the final expression that one wanted. This expression gives the so with this in hand, one can compute. Now, as I said, there is no particular significance of this. It's just a way of explicitly, if one is given a vector field in turn local coordinates, one can use this to calculate the Lie bracket. Now, returning back to Lie brackets of, let's talk about Lie brackets of left invariant vector fields on a Lie group G. So we have seen that the crucial property is that we have seen that if two vector fields are F related under some smooth map F, then the Lie brackets of those two vector fields are also F related. Let us use that to prove the following. Let x and y be in the space of left invariant vector fields on G, which I have denoted by this script G, B. So let x and y belong to this, then the Lie bracket is also belongs to this. In other words, the Lie bracket is also left invariant. And this follows immediately from the fact that the property of being F related transfer over to Lie brackets as well. So now notice, so the main point here is that X is left invariant if and only if X is LG related to itself, i.e. see the left for any G, for any G in G. So LG is a map from the Lie group back to left translation is a map from the Lie group back to itself. And what we are saying is that so there is X here and there's X here as well. So X is LG related to X. So what does this mean actually? So going by the definition of F related, so this just means that D LG at a point P acting on XP equal to X at LG of P. This is the meaning of being LG related. So a vector field is LG related to X if this happens. But the right hand side is the same thing as X. Left translation is just GP. So now if you look at this equation, DLG at P acting on XP equal to XGP, this we have seen is the same thing as the vector field being left invariant. We have used this several times. So therefore this property of left invariance can be expressed in terms of the fact that LG related to itself. Therefore, if X and Y are left invariant, then i.e. X and Y are LG related to X and Y again, then the Lie bracket XY is LG related to XY. Actually, the therefore here is not appropriate. So this is so LG related to XY. Here therefore XY is left invariant, and this is for any G. For any G in G. Therefore XY is left invariant. So this is a very important thing, because now we have already looked at the set of vector fields on a Lie group and left invariant vector fields, and we have seen that it's a finite dimensional vector space which is naturally isomorphic to tangent space at identity. In particular, it's a finite dimensional vector space. But this proposition shows that it's a finite dimensional vector space with an additional algebraic structure on it, namely that therefore this G is a vector space with an additional algebraic structure, namely the Lie bracket. So this is a map from G cross G to G, and in fact moreover this is the Lie bracket of vector fields. One has let X, Y, Z belong to be vector fields on any smooth manifold, not necessarily a Lie group, then X, so I can take X, Y, Z. It's like associativity doesn't hold. So the Lie bracket of vector fields is not associative, but instead one has this property X, Y, Z. You cyclically permute these things, Z xy plus and then y zx equal to 0. So this is called the Jacobi identity. This equation is called the Jacobi identity. So the Lie bracket, we have already seen that it is antisymmetric and bilinear. Now here's one more additional property of Lie bracket of vector fields, and this is true on any smooth manifold. So this, I won't prove this. This is a direct consequence of the definition of Lie brackets. So one can act it the whole left hand side on some smooth function f, then simplify the expressions. So but the point is that returning back to the case of left invariant vector fields, we have the set space of left invariant vector fields on a Lie group is a vector space with a bracket operation which is bilinear, antisymmetric and satisfies the Jacobi identity. Now such a thing has a name. Definition: let V be a vector space and suppose I have a bracket as a map which is satisfying the following three properties. One is first is this map is bilinear. Second thing is that this map is antisymmetric. Lie bracket of xy should be equal to minus Lie bracket of yx. Third thing is this Lie bracket satisfies the Jacobi identity. So any such vector space V is called a Lie algebra. So in other words, we have talked about the Lie algebra of a Lie group, but this notion makes sense in a very general setting. Whenever you have a vector space with this bracket operation, we can define a notion of a Lie algebra. And the two examples we have in mind are the Lie V equal to the set of smooth vector fields on a manifold, and this is not a finite dimensional vector space, but the second example we have is G, the left invariant vector fields space of left invariant vector fields on a Lie group. What we just showed is that this left invariant vector fields, if I take Lie bracket, we again get left invariant vector fields in the left invariant vector field. So this closed under the Lie bracket operation, which comes from the more general Lie bracket of vector fields. The third example is, let's look at the set of n cross n matrices, and let's define the Lie bracket of xy to be just AB minus BA. Then one can easily check that this is a Lie algebra as well with this. Now what I am going to show now is that this actually, the third example is not anything new. In fact, the third example arises from the second one, the space of left invariant vector. For an appropriate choice of a Lie group, this is a special case of 2. In other words, MNR. So let's do that now. Example of Lie bracket. So examples of Lie bracket. So let's do it for the basic Lie group that we know, namely GLNR. So G equal to GLNR, the set of invertible n-cross-n matrices. We know that, so here's the claim. Yeah, the claim is, if we identify the Lie algebra G with the tangent space at identity of G, which is MNR, then if we identify this, then the Lie bracket of AB is equal to AB minus BA. So let's prove this. So this is what I said a few minutes earlier, that the third example is a special case of 2. So if we take the Lie group to be GLNR, the set of left invariant vector fields which is identified with the tangent space, and it's MNR. So, and the point here is that the Lie bracket operation coming from vector fields is the same thing as this matrix operation AB minus BA. So for that, we'll need a few lemmas. So the first lemma is that, let's first describe what a left invariant vector field looks like. I want to understand this identification more clearly. So let me take A in MNR, which is the tangent space at identity, and let XA denote the left invariant vector field on G, left invariant vector field on G with whose value at identity is exactly A. This is how this isomorphism arises, that you start with a left invariant vector field, see what its value is at identity is, so you get an element of the tangent space. So conversely, starting with this, I can get a left invariant vector field, so which I've denoted by XA. Right. So now what I want to do is, I want to describe XA at any point. This is at identity, it's A. So I claim that XA at any point P, then XA at P is nothing but PA. So this is the first. So this gives a very explicit description of any left invariant vector field. So proof is quite simple. So, well, by definition, XA at P is D, the left translation by P. So this here, of course, P is any for all P in GLNR. So by definition of the left invariant vector field with value A, so XA at P is equal to DLP at identity acting on A, the value of XA at identity, which is A. So we have this is by left invariance. Now, so let's look at this map DL. So we want to understand the derivative of the left translation map. We don't have to do any computations, because what we observe is, note that the left translation map, which is a map from GLNR to GLNR, is actually the restriction of the left translation map from MNR to MNR. And the point of regarding it as a map on a bigger space is that this left translation map on MNR, this LP is a linear map. So LP of n, remember that LP of A is just PA. So it's of course linear in A. So it's a linear map. Therefore, the derivative of LP at any point Q is equal to just the map itself at any Q in MNR. So, and this we have seen just from the definition of a derivative in Euclidean space. Now here we are in the realm, and we know that the notion of a derivative when we are in the realm of Euclidean spaces, whether we use the original definition or the abstract manifold definition, we get the same thing. So this DLP at any point Q is just LP itself. Since GLNR is open in MNR, the derivative of LP is the same as what it would be when I would regard it as a map from MNR to itself. DLP of Q is equal to LP for all Q in GLNR as well. So this is the advantage of regarding it as a map of a vector space. And once we have this, and this Q can be anything, not necessarily the identity, though here I'm mainly interested in identity. So, but it's the same thing. So what I get finally is that therefore XA at P equals DLP at identity of A, and this is the same thing as LP of A, and by definition this is PA. So one is done. Right. So that's the claim. So we have proved the lemma that the left invariant vector field is just given by multiplying the A with P. That is one thing. The second thing is that with that in hand, now we can proceed to show that, we can proceed with our calculations and show that use this to simplify the computation of the Lie bracket. Okay. So I'll have to stop at this point since I'm out of time. I'll resume with the calculation next time. So thank you. We'll resume at this point in the next lecture.